Welcome back. We are almost at the end of the lecture. Almost, but not quite. And we have a relatively difficult concept to think about, which is amorphous materials. So, good and bad news there, but I thought I'd start with the good just to make you feel better. We have to talk about the amorphous state. What is the amorphous state and why is it difficult to understand? Well, the answer is it's very difficult to define. As scientists, we like to define things. That's the point of the unit cell. We can define where the molecules are and then we know where everything is and we're happy. The amorphous state is, on the other hand, a random state, and as a consequence it is very difficult to define. There is another issue with the amorphous state, and that is that we're considering amorphous pharmaceuticals. And amorphous pharmaceuticals are kind of unusual actually, but there are some other sectors of chemistry where amorphous materials are much more common. The polymers industry in particular. Think about that. Amorphous means not crystalline, for want of a better phrase, and polymers are huge great molecules, and so polymers find it very difficult to crystallize because they're so massive. It's very difficult to imagine how a polymer of molecular weight 200,000 is going to line up in a repeating pattern, and so they don't, and so they become amorphous. And so some of the terms that we use to describe amorphous materials have originated in the polymer field, and so although we use the same terms, it's kind of difficult to see where they come from because we're trying to apply them to drug molecules, but they're usually applied to polymers. But bear with me and at least we'll see if we can understand some of it. So a lack of understanding of what they are and a definition is one problem. The other one, which is quite an issue, and it's one of the things I hope you're not going to do if you end up working in the pharmaceutical industry, is that a lot of people don't understand what an amorphous material is, or they don't understand that something that they're doing might make a material amorphous, and so they're never looking for an amorphous material. The expectation is that your material is crystalline, and if it's not behaving itself properly, people tend to think, well, I must have made the wrong crystal structure or something like that. They never consider, oh, did I actually make the material amorphous? Because they don't recognise that some of the processing techniques they're using can make the material amorphous. So if I give you some examples, spray drying, freeze drying, even compaction to make tablets, anything where you're applying a kind of force to a material, that can make your material amorphous. And so people are using these processes in the pharma industry. They don't recognise that they might be making their material amorphous, so they're not looking for amorphous material. And sometimes you can misinterpret the data that's in front of you because you're not considering a really important factor, which is this thing that the material might not be crystalline anymore. I have to say that in the pharma industry, if you're spray drying or freeze drying, most people know that those techniques make a material amorphous, and they generally make the material completely amorphous. And so usually spray drying and freeze drying is kind of looking for amorphous materials because that's what your expectation is, especially with freeze drying. You know, freeze drying is used to make powders for injection, for instance, or fast melt tablets. You know, those are deliberately made to be amorphous in order to act properly. We might look at that later on, not in this lecture though. Whereas compaction, for instance, it might make the material only 1 or 2% amorphous, and so if you're trying to look for it, you don't see that it's amorphous, but it can have an effect. People don't think about it. So that's a bit of a problem. However, we do need a definition. Definitions are kind of important. So this is my definition of an amorphous material, and you're free to argue with it if you like. My definition is it's a material that has the molecular structure of a liquid, but the viscosity of a solid. Okay? Easy as that. The molecular structure of a liquid, but the viscosity of a solid. Or another way of thinking about it actually is to say it's simply a high viscosity solid. Okay? What do I mean by that? I mean, if we looked at a crystalline material like we did earlier, all of the molecules are arranged in a repeating pattern. Okay, that's why it's a crystalline structure, lots of pattern. If we look at a liquid, you can't see, but there's a cup of coffee in here. If I was to look at the molecules in my cup of coffee, they are all going to be randomly distributed, and moreover, they're going to be moving. Okay, so when I look at the structure of a liquid, I can't say where my molecules are. One, because there's no pattern, so they could be in any orientation, and 2, they're constantly moving. So even if I defined where they were, a millisecond later they're somewhere else. And so there's no point defining. It's a moving goalpost, for want of a football analogy. And that's not good. Clearly, my cup of coffee is a low viscosity liquid. That means if I apply a force to this material, the coffee is going to flow away from the force that I'm applying. You knew that at some point I was going to get rheology into this class because I like rheology so much. So low viscosity material, Newtonian fluid as well, if you're thinking about it. I push the material and it flows away from me. So when I say an amorphous material has the structure of a liquid, I mean the molecules are randomly oriented, just like they are in my coffee. But when I say it's a high viscosity liquid, I mean as I apply a force to that material, it does not flow away from me because it's kind of stuck. All the molecules are stuck in place. So think of it like a high viscosity liquid, and then you'll be on the right line. Have you ever come across an amorphous material? Do you think you handle amorphous materials in day-to-day life? On the screen are some examples of amorphous materials you may have come across. Anyone that wears these, I normally wear these to teach, but not when I'm talking to a camera. So glass is an amorphous material, for instance. Jelly babies on the screen are amorphous materials. Chocolate, which you can see on the screen, is also an amorphous material. So you do come across amorphous materials in day-to-day life, and we use them in pharmaceuticals as well. This graph, it's probably the trickiest part of the lecture, and it's kind of a shame that it's coming towards the end actually, because your brains might not be concentrating on what I'm saying anymore, in which case I highly recommend pausing the video, watching a box set of something on Netflix, and then coming back again when you feel energized, because this graph is reasonably complicated in terms of understanding, but everything to do with amorphous materials is encompassed in this graph. Okay, so I'm going to talk through it. If you're not quite clear, same as before, just pause the video, go back, play it again, write me an email, whatever. Just try and get your head around it. So what this graph is doing is explaining to you what happens to a material when we cool it down in temperature. So imagine that we start on the right hand side, high temperature. The material is above its melting temperature, and therefore it's going to be a liquid. So where it says Tm on the x-axis is the melting temperature. If you're at a temperature to the right of that, a higher temperature, the material is a liquid. It is not a solution. Okay, it's a liquid, a molten material. So it's a liquid. And then what this is showing you is what happens as you cool the material down. So usually as you cool a material down, the molecules start to move around with less energy, and they tend to therefore occupy a smaller volume. So on the y-axis of this graph, there's the word volume. You could equally write the word energy on the y-axis, and I frequently do actually, because it's also losing energy as the material cools down, and sometimes I find that easier to explain what's going on, but for now we just stick with volume. So as we reduce the temperature, the volume of the material starts to reduce, and so we see this line coming down. If the material can crystallize, and it can crystallize to the stable form meaning the one that's most perfectly packed, there will be a drop in volume it's at the melting point. But remember, melting point is what happens on the way up as we increase the temperature. When we cool the temperature, the material actually condenses to form a crystal. So on the way down, at the melting point, the material crystallizes, and if it crystallizes to the stable form is the one with the lowest volume, and so there'll be the biggest drop because it's the one that's going to the smallest volume. And then after that, the material will carry on reducing in volume as the temperature reduces. But we will see this for crystalline material. The question is, what happens if we cool the material down quite fast? I'm sure that you can imagine this, but imagine that each of my Lego bricks is a molecule, not a unit cell now. Imagine that each one of these Lego bricks is a molecule. Okay, then when they're in the molten state, the bricks are all free to move around. That's fine. When we get to the melting temperature and we're cooling down, they have to condense to form a crystal. And so to do that, each molecule has to line up with the molecule next to it. So you can see, I hope, that this is taking a degree of time. I have to put each molecule in the right place in order to form the crystal. So to grow the crystal takes a period of time because each molecule has to be in exactly the right position. If we cool the material down really slowly, that's fine. When we get to the melting temperature, there's lots of time for the material to crystallize and it should be okay. The question is, what happens if we cool it down really fast? So imagine we drop the temperature really fast. Then what will happen is all of your molecules, I'm going to create a molten material again, all of your molecules which are floating around in solution are reducing in temperature really fast. As they reduce in temperature, they're losing energy. As they're losing energy, it means they're moving around more slowly. If, to make a crystal structure, all of the molecules have got to move in order to crystallize, and we reduce the temperature so fast they can't move, they can't crystallize. The molecules can't move to crystallize, and so they remain as a liquid state. And so on that graph, as you come, I should go this way. As you come down and you go past the melting point, the next region of that line, the material is still a liquid, okay, because it hasn't crystallized. The molecules are still randomly distributed, but now it's a liquid below its melting point, and that's called a supercooled liquid. So that region of the line, melting point, the next region here, the material is a supercooled liquid. It has the structure of a liquid, but it's starting to become more viscous because it's reducing in volume. If that was to carry on, that process was to carry on forever, then as you cool the temperature, you would carry on down this line. You've got the bottom line, which is the position of your crystalline solid. You've got your supercooled liquid. If that was to carry on, there's going to be at some point a crossover between these two where the volume of your liquid-like structure is less than the volume of your crystal structure. And in practice, that can't really happen. It's not possible in nature to have a liquid-like structure occupying a lower volume than a perfectly packed crystal structure. So something has to happen to the material to prevent the supercooled liquid line from crossing over the crystal line. That region is shown dotted on the graph, the dotted purple line. So what actually happens is the material goes through a discontinuity. So I hope you can see that you have a supercooled liquid, and then at one particular temperature called the glass transition temperature, there is a discontinuity and the line goes like this. This is what will happen for real. If you actually measure these properties for real, this is what an amorphous material looks like. So at this very particular temperature called the glass transition temperature, there is a discontinuity and the material becomes a glass. Now you might have heard of that term glass, principally because I just showed you an example of a glass. A glass is a high viscosity liquid. Okay, very high viscosity. It's not moving as I'm applying a force to it, but it's still a liquid, which is why I can see through it. Okay, so the material becomes a glass. So it comes down like this. It's a molten liquid, a supercooled liquid, then it becomes a glass. Why? That's the tricky bit. Why does this happen? What happens at the glass transition that causes this discontinuity and the formation of a glass? And this is where it becomes slightly tricky. So the way that I normally explain it is to think about volume and to think about viscosity. So in your material, you have a certain number of molecules. It doesn't matter how many it is, it's a lot, but there's a fixed number of molecules. And when you're on the right hand side of this graph and the materials are all free flowing as a liquid, the molecules are all free to move around and bump off each other. The volume is high because they've got a lot of energy and they're bouncing off each other. As we reduce the temperature, the volume is reducing because they've got less energy. So they're not bouncing off each other with quite so much energy. The volume is reducing. The volume is reducing, but the number of molecules is the same. Imagine that you're on a tube going home, not in the pandemic because there's no one on the tube, but on a normal London workday, you're on the underground and there's thousands of people on the Metropolitan line and you try and cram into that carriage. The more people there are in a given volume, the harder it is for you to move around. And the same is true for the molecules here. The more molecules there are in a given space, the higher the viscosity is going to be, because the molecules keep hitting each other. Imagine that you're on the Metropolitan line and you're thinking that the train is already relatively busy, and then there's an announcement from the guard that something's wrong with half the train, so they remove half the carriages. The same number of people have now got to get in half the number of carriages. You're going to be wedged into that carriage, and the person next to you is not social distancing. You've got no room to move. The viscosity is going to become higher, and the same is true for the molecules here. As we reduce the temperature and they become a supercooled liquid, the volume is constantly reducing. Because the volume is reducing but the number of molecules is the same, the viscosity of the material is getting higher. So the way that I like to think about it is that when we get to the glass transition temperature, we reach the point where the viscosity becomes so high, as we try and push that material, it no longer can flow. So think about it. On the right hand side, above the glass transition temperature, the material will move as we apply a force to it, but below the glass transition temperature, the viscosity is high enough it's become like a rigid solid. That's the easiest way I think of thinking about it. Structure of a liquid, viscosity of a solid. Okay. Below the glass transition temperature, the material is said to be a brittle glass. Brittle because if you would hit it in some way it would shatter. And above the glass transition temperature, while it's a supercooled liquid, it's said to be a rubbery amorphous material. So rubbery above the glass transition temperature, brittle glass below the glass transition temperature. Now, at some point in the future, if you decide to stay beyond your MPharm and you do, say, a master's degree, or maybe even a PhD, which is kind of a good idea if you're into that sort of thing, then you can do some option courses that we run for master's students. And I run a master's course on amorphous and crystalline materials, and we go into huge detail in this graph. And if you're interested about the graph, you can always talk to me about it, because there's a lot more that goes on in this graph than the very simple view that I've just given you. But for now, also, if you look in my textbook that I talked about earlier, there's a whole chapter on amorphous materials and this graph in particular. But for now, I think the easiest way of thinking about it is that the material is molten, you reduce the temperature, it can't crystallise because you're reducing the temperature too fast, it becomes a supercooled liquid. As the temperature drops, the viscosity is increasing, you get to a critical point at which the viscosity means it becomes like a solid. That's the glass transition temperature, and below that temperature the material is a glass. Okay, if you want to discuss it with me, fire me an email. Maybe we'll have a workshop and we can talk about it. Right, so on the screen you can see some characteristics of amorphous materials. The number one characteristic of an amorphous material is that it has a glass transition temperature, because that's how it was formed in the first place. Below the glass transition temperature the material is brittle and it's solid-like, as I said already. Above the glass transition temperature the material is rubbery, but it's still a liquid. Now, what does rubbery mean? I tried to find an elastic band, but I couldn't find one. So you've got to imagine this next section. But if I said to you, what is the physical form of a rubber band? Is it a solid, a liquid, or a gas? I hope you'd say to me, it's a solid. So a rubber band is a solid. And I'd say, absolutely, a rubber band is a solid. But also, it's a very flexible solid. So if I were to take that rubber band and I was to stretch it, let go, and ping you with it, it will recover its original shape and it will cause it to move across the room and smack you in the face. So a rubber band is clearly a solid, but because it's a rubbery solid, it will move as you apply a force to it, and the same is true here. And material above its glass transition temperature is rubbery, it will flow as I apply a force to it, and below a glass transition temperature the material is brittle. Why is this important for pharmaceuticals? The answer is it goes right back to the candy floss that we talked about at the start of the lecture. So candy floss is amorphous sucrose. Okay, it's a high viscosity liquid form of sucrose, and so if you think about dissolution, as we said already, if you've got the stable crystalline form, you've got to break the bonds that are holding the molecules in that crystal form apart in order to get the molecules into solution. If you have a metastable crystal form, You've still got to break these bonds, but the amount of energy that you put in is less. Think about the amorphous material as being the most metastable form that you can have. It's kind of got, it's kind of like a solid, at least it feels like a solid to you because it's got a high viscosity, but actually there's very little holding the molecules together because they're so far apart. So the amount of energy that you've got to put in to break it apart is almost zero. There's very little holding an amorphous material together. So if you think about the thermodynamics that we talked about earlier, the first step in dissolution is putting energy in, which was endothermic, and that was really not good from the thermodynamic perspective. For an amorphous material, that stage is almost zero. So there's almost no endothermic input of energy required. It's all exothermic as the material interacts with water. And as a consequence, because that energy is the lowest, to break that apart, instantly the material is going to dissolve, and it will dissolve very fast and usually to a higher concentration. So if I'm making an amorphous pharmaceutical, that's great, isn't it? Because what should happen is the patients should swallow it. It will either disperse in their mouth or at worst by the time it gets into their stomach, and we should get relatively rapid bioavailability. It's a really good way of formulating drugs which have got really poor solubility, is to make them amorphous, and you can make them dissolve faster. Are there many products on the market that are amorphous? The answer is no, and the reason, as I've alluded to already, is because the pharmaceutical industry is governed by stability, and the stability of amorphous materials is usually quite bad. There are some ways that you can make amorphous materials more stable. Freeze drying is one that I've said already, but you can also add polymers to try and prevent the drug from moving and crystallizing. Those are called solid amorphous dispersions, and we're going to talk about those later on in your degree. But for now, at least, remember these basic principles, which is that crystalline material is going to be the most stable but the hardest to dissolve, and an amorphous material is going to be the least stable but the fastest to dissolve. And so when you're trying to make a product with a particular characteristic in terms of bioavailability, you kind of need to consider how fast do I need it to dissolve. If I need it to dissolve very fast, the chances are it needs to be amorphous. If the dissolution rate is really not a problem at all, then it can be the most stable crystal form. Okay? Right, we are at the end. That's 4 sections of really complicated stuff, and I really hope that you've managed to follow at least some of what I've been saying. And if you haven't, I highly recommend that you get down to the library and read one of the 2 textbooks that I recommended. In summary, so I put a summary on the screen. In summary, it's really important to understand the physical form of the material that you're formulating for multiple reasons. The number one reason is because if you don't, you're not really in control of the stability of your product. And the pharmaceutical industry is governed by stability. If you make the most stable crystalline form, your product is as stable as it can be. It does not mean that it will never change. A material can still chemically degrade, but in terms of its physical form, it can't change because it's got nowhere to go. So remember, the most stable crystalline form is going to be the most stable on storage, but it's going to be the worst performing in the body because it will have the slowest dissolution rate and the worst bioavailability. Okay? If you want to improve the situation and the material is polymorphic, polymorph means you've got more than one crystal form available. If it's not the stable form, then it must be a less stable form, and less stable is called metastable. So a metastable polymorph will dissolve faster and give you a higher bioavailability, but on storage there is a risk that it will crystallize to the most stable form and you lose that product performance. And then in the limit, an amorphous material has no structure, it's a high viscosity liquid, and it will dissolve the fastest to the highest bioavailability, but the chances are on storage it's probably going to crystallize. Right, and with that we are done. If you have any questions, fire me an email. Otherwise, I will see you in a couple of weeks' time for another lecture on drying, I believe.